Hopefully, okay. Just kind of a quick introduction. I just simply go by Professor Hacker, but most people call me Professor Esconda here. At US, we normally use last names. I've been teaching here at UniKL for about the last 8 months or so, not quite a year. I've lived in Malaysia about a little over a year. The first 6 months I was in Malaysia, I actually worked for Mike down in Cyberjaya, which is a government there. I taught in Malaysia back about 18 years ago for 2 years. Then I was at what's now UTHM for a year, and I was at Uniten for a year. Most of my teaching career, however, has been back in the U.S. at Purdue University, at one of the campuses there. Some of you have heard of Purdue University, many of you have not. It's a big school, large engineering school in the U.S. They have about probably 6 campuses across the state, of which about 3 or 4 are relatively large. And I was at one of the larger campuses. The Fort Wayne campus had about 13,000 students there, and I spent about 30 years there, counting the 2 years I was teaching in Malaysia back in the 1990s, because I was a Purdue employee on loan to both UTHM and Uniten. Prior to that, I've worked in the microelectronics industry, and even while I was teaching, I worked pretty much half-time most of my career in the microelectronics industry as either a consultant or a design engineer doing various design in both the microprocessor area and the FPGA or custom digital logic area that's there. So I've done a lot of VHDL programming, I've done a lot of assembly language programming, a lot of C programming, along with hardware design in those areas that's there. So I come here with a lot of industrial experience there. I'm not necessarily so much of a instructor in the aspect that grades are not as important to me as maybe some of the other instructors go. So if I seem a little lackadaisical about worrying about grades, it's because I personally feel grades are not important. That there. Of course, I will assign grades at the end of the semester because that's part of my contract is that I have to assign grades, and I will give you a final exam that's worth 60% of your final grade and everything else that's there because that's part of that there. So typically, when I've taught this course in the U.S., and I'll refer back to that from time to time, I did not give exams. That tells you what I think about final exams. But unfortunately, the system here is exam-based. And the reason I don't like final exams is because I've hired engineers in the past, I've fired engineers in the past. I've hired professors in the past, and I've fired professors. I've worked in management during a lot of my career out there. Not once did I fire somebody for not passing a final exam. Not once did I promote somebody for passing a final exam. Nor did I hire them because they could pass a final exam. Final exams are only in the academic world. You're going to graduate and get real jobs. Inshallah, that's the goal, right? And when you get a real job, you're expected to perform certain tasks that require certain skills. My job here is to give you some of those skills. I can't give you all those skills. The university can't give you all those skills. The skills that I can try to get across are technical skills in how to deal with microprocessors, what they are, how to look at least understand them. This is a one-semester course. Unfortunately, there is a fair amount of software in this course. That's there. And microprocessors live on software. That's there. That's the way what they're based on. Now, I've redesigned this course a little bit to take some of the hardware out of the course and kind of jump us a little bit more into the inner workings of the microprocessor and how they work, and not talk so much about interfacing to outside components. And I'll get into that in here in a little bit as I start going through the slides. Previous versions of this class used a microprocessor called the 8086, and let me kind of talk about the changes that I've made to this class over the previous version. Is that the 8086 is a standard microprocessor, and we'll talk quite a bit about the difference between a microprocessor and a microcontroller. And we'll be using a book for this course. I will be posting it on up there. Let me just kind of put this up there. This is actually a set of slides I stole from another university that I'm going to use for the first few lectures. I tend to steal slides from various places and use them. I don't spend a lot of hours typing up slides. I have, but these courses are still somewhat dynamic. In other words, I'm not sure where they're going to end up yet up there. So instead of typing a lot of slides that I may change later, I'm just going to steal for now. And I think it was Steve Jobs that once said that good innovators copy, great innovators steal. Out there, I don't know if anybody's ever heard that quote before. Actually, Apple computers, Steve Jobs and Apple is quite notorious for getting upset with Microsoft and suing them for copying the Windows interface and everything else. What most people fail to tell you is that Apple actually originally stole that from Xerox. So they were suing Microsoft for stealing the idea that they stole in the first place. That's there. So I'm telling you right now that I stole this guy's slides and I'm going to use them. Since he posted them on the internet and said use them, I'm going to go ahead and use them. Right there. So, and there's nothing wrong with that. It's okay to use other people's work as long as you give them credit for it. That's there. That's there. And add something to it. If I just show these slides and didn't add something to it, then I bring no value to the table. That's there. So I set up some ground rules. I set up a Facebook page for this class, and I'll show that at the end of the class, where I'll put the slides that I use for each class up there, along with links to the videos. I recorded all my lectures and I post them on YouTube. Up there. And welcome to our latecomers. That's there. First day, I'm not taking attendance, but sooner or later, I will. I will try to start as close to 3 o'clock. Now, normally during this time slot, there will be a lecture, a lab. Now, as I look at my schedule, and let me look at my schedule, I'm looking at this room, and it's quite full here. And let me see something here as I look at my timetable. Give me a second here. Right here, look at my timetable. Right here. Timeline. Oracle report. Okay. This is NEB 20203. This is a lab for the course. I have another group just like you that meets right after you, right there. So this is lab group B01, and then I got lab group B01. This is 02, 01 meets after this one. The lecture for this course is actually tomorrow it's in room 330, which is upstairs. It's a large room. So normally what's going to happen is during this time I will be having you do labs. Obviously, we have not done any lectures yet, so I'm going to give a lecture today, and I get the wonderful privilege of repeating the same lecture as soon as I end this discussion. Maybe what I should do is just put the video up and let them, and then I go have dinner, right? That's there. So normally during this slot, we will be doing labs right there. We won't necessarily have labs every week, but I also have a bad habit of only lecturing about an hour and 15 minutes to an hour and a half. I have just discovered that after about an hour and 15 minutes, most students tend to either start dozing off or they tend to drift away. My voice starts to go downhill, and especially when I got two of these back to back. Plus I had another lecture earlier today. So Mondays I've got 6 hours of classes. So and I do it on Tuesday as well. So I've got a heavy load this semester. So normally we will be doing labs. In a more perfect world, I would have a lab kit for every group, for every student, that I would just give you at the beginning of the semester. You would take it home and you can do labs at home. Unfortunately, I don't have that many because I've got 3 groups using it. I have enough boards that each student in the lab can do the lab. So I will be issuing a board. The boards we're going to be using for the labs are very very small. They're very inexpensive. I put this course together based around the 8051 microcontroller, and we'll talk a little bit about that. So this is the lab board right there we're going to be using. They're relatively inexpensive. It's 40 ringgits for that and the programmer. To do the labs, though, you have to have these. There is no simulator for this particular microprocessor. There is, but I choose not to use it. I'd rather work with hardware. And the reason is that it's easier for you to see things working in hardware than it is to that there. Now, some of the early labs won't make sense, but when we turn the LEDs on and off and read the switch, yes. You want to see me after this class? Okay. Walaikum salam. That's there. After this class or my next class, I got 2 back-to-back. I'll go see you right after this class. Okay. You're in the next lab? Okay. I think is he the campus troublemaker? That's there. No, he's a good guy. That's there. So, all right. That's there. So I will have a series of labs read. Some of the labs won't take 2 hours to do, especially some of the early labs, because the first lab is just plugging the board in, running a program, seeing that it runs, see the process of how to hook it up. That there. And we'll do that next week. What I will normally do is during my Tuesday period, which will be tomorrow, I will show you what the lab will be for the following week. So today, I just simply get to repeat the lecture twice. That's there. So let me kind of just jump into these slides. A lot of these slides are introductions right here. This is not a PowerPoint. This happens to be a PDF file that right there. And I'm kind of going to go through a little bit of this. I'm not going to worry too much about some of this. One of the things that we do need to know, and I'm going to spend maybe a little bit of this hour talking about it, is we need to know numbering systems right there. That's there. I know that I'm teaching 106, whatever it is, 01 or 03, whatever it is, the digital course right now, and numbering systems is covered. That was about a year ago for most of you, right? Or last year? That they're basic. That they're. So we will be working with hexadecimal numbers for most of our classes. So that there. So and I'm not going to spend a lot of time on that because it's important that you've had it, that you've seen a review, but we won't do it a lot. Use it for a lot of things here, right there. So all right, just kind of get back to a little. The idea is that basic people use basic 10 decimal numbers are set up on the idea of 10 unique units. The reason we use unique 10 is because we have 10 fingers. The early man or woman could only count with 10 fingers, so they didn't have 16 fingers, so they didn't use base 16. We use base 10. Now, if you look at the early numbering systems, there's lots of early numbering systems. The first one that I can think of was the old Roman numeral system, which was a total pain in the neck to use. You ever want to see what a pain in the neck to use Roman numerals is? Just write a program to convert Roman numerals to regular numbers or back and forth. Roman numerals are relatively awkward to use. The Indians had a relatively nice numbering system, but it didn't have a zero, so that causes some serious problems. When the Arabs added the zero to what is now our current numbering system, which was based in Arabia, somewhere right around the time of I want to say about 700 comma error, or about 100 years after the Prophet or so, that they introduced the concept of using a zero, and that's where our current numbering system came from right there. So if you look at Arabic numbers, you look at what we currently use, they're about the same numbering system. And that's really the establishment of base 10, is that we have 10 that there. So when you add 15 to 9, you get a 4 with a carry out the 4, so you get 14. So typically computers use only ones and zeros because transistors are either turned on or turned off. TTL logic is on or off. That's there. So it's kind of asking the question, are you married? It's a yes or no answer, right? That's there. Although in Malaysia, I hear the term is they're married but available at some menus, right? Because of the in Western cultures, you're allowed one wife. Here, I hear the term, married, but that's okay. But regardless, the answer to that question is usually yes or no, right? Are you a man or a woman? Yes or no. Computers have 1 or 0. They're on or off, any output that's there. So, and that's in all TTL logic right there. So I'm going to skip over this, how to convert back and forth. It's not really important that you know how to do it in this course. I'm teaching basic. I taught basic digital for the transfer degree students. I'm teaching it now. I guess that's picked up to be one of my classes. So in the basic digital course, I can really pound numbering systems in. So I'm not going to spend a lot of time on it here, right there. So, and if you need to convert back and forth, Windows has a calculator that allows you to do that. They took it away with Windows 8 and they brought it back with Windows 10. But there's a really nice, neat little calculator with Windows 10 that if I want to, Windows 10 has got a nice little calculator. I can put it in programmer mode right here, and I can say whether or not I'm in decimal, 52, and then I can go ahead and hit hex right there, and that's my hex output for that. I can put in the number 11001111, for example, and that tells me that that's decimal 207. It also gives me the hex for that number right there. So converting back and forth is not something that you really need to spend a lot of time learning how to do that there. I know in digital you probably hated the instructor who did that. They probably really harped on that. It was on the final exam probably and things like that. And now I'm saying that real programmers just use the calculator built into Windows right there. And if you're running Linux, there's a similar calculator that does that there. So, or if you're using an Apple, so you could convert that there. And note there that there's 4 different numbering systems on this calculator. That their hexadecimal is the most commonly used, because hexadecimal is bit for bit or a 1-to-1 translation. You don't have to do any calculations. 1100 is always going to be C. 11111 is always F. 1010 is A. 1001 is 9. And after a while, you start to memorize them. So going between hexadecimal and binary is very simple, and that's why people use hexadecimal, because you make far fewer mistakes. It's a whole lot easier for me to write CF than to write 11001111 and not make a mistake right there. So that's the reason we use hexadecimal right there. And this particular one, we can change this from a quad word, double word, and change the size right there. So again, I'm not going to spend a lot of time. The slides go through this. There in your basic digital book, you went through that there. There's ways of converting right there. Here's the hexadecimal system. I would expect that you would be able to go from binary to hexadecimal and back and forth easily right there, which means that you may have to cheat and put this table down on a piece of paper or whatever. This table is fairly easy to come up with. 0101010011, 4 zeros, 4 ones, 8 zeros, 8 ones, like that there. And then you just 0 through 9 and then A through F right there. That's the hexadecimal binary table, and it's a 1-to-1 translation. So if I have the number 3E2A, it would be 3E. It would be 0001. E is 1110. 3, what did I say? 03A up there, but you would just look it up. You would just look it up that there, and that's the way that you would convert from hexadecimal to binary. If you want to go from hexadecimal to decimal, then you typically would just use the calculator. Now, when we write our programs, we can write in either hexadecimal or decimal or binary. We can do, we have the choice of specifying which format we want to use that there. So, again, here's an example, is they give 8, 9, 6 right there. And as I didn't even look at the answer. I could see I can do the translation by inspection that there. Like, I don't expect most of you to do that. I expect most of you to look at the table in order to do the translation. If you do it a couple hundred times or a couple of 100,000 times in your lifetime, like I probably have done, then you probably can do it by inspection right there. But by the end of the class, you won't be so good at it that you can do it by inspection. You won't do it that often right there. They go through that there. Again, this is just simply the format converting, a couple of examples, and I'll post these slides up there, right there. So, right there. And again, they say the easiest way is to convert the binary, then convert to hex. I say the easiest way is to use a calculator. Anytime you're wanting to deal from decimals to either hex or binary, use the calculator on Windows. And that will not be on the final exam. So you don't have to bring your computer to the final exam. Right there. Although many people would wish that you would, but you don't want open test. You don't want open book and open internet finals. Boy, I could write those so hard that nobody passes them. That's there. You should prefer closed. That's there. So I'm just going to kind of skip through these numbering systems right there. All these slides are there for review. And they're, now, depending on who you had for digital, you may not have talked about what's called an ASCII code. Before I go any further, let me give a quick definition here between a numbering system and a code. Numbering systems means that we can add, multiply, divide, subtract, perform all kinds of arithmetic operations. Codes, you cannot do that with. Codes are essentially that. All a code here, in the case of an ASCII code, means that the capital letter A is represented by the hex number 41. Why is it 41? Who knows? I have no idea. The person who wrote the code down started at 00 for the null character and just started writing down all the characters that need to be sent to a teletype machine. This was developed way back when teletypes were back in the 1950s. Is how long this has been around. Before I was even alive, and I've been alive for a long time. That's there. That's there. And basically all the various characters, and they put the uppercase letters before the lowercase letters there for whatever reason. They're exactly 20 hex digits apart from each other. So capital A is 41, lowercase a is 61. Right there. That there. And you cannot add two ASCII characters together and get the right answer. And when we start sending stuff to printers and using printf commands and things like that, there's a difference between the character 1 and the number 1. They are not the same. So if you're dealing with a character, and you should have seen this in your C course, right there. Something is defined as a %I is an integer. That's a number between 0 or negative 32,000 something or other, all the way up to positive 32,767, right? But if it's a character C, that means it's a number between 0 and 256, which would equate back to a character in the ASCII code. So in C, you would have seen the ASCII codes to a degree. You may not realize that there. Did they talk about the data types %C or char when you took C? And a string was a array of chars. So if we wanted, for example, put a string in, it would be a series of numbers, and that's how data is stored in a computer system. That if you have a text file, it would be an array of numbers. Each character in your text file, including the character return line feed, is a character in the ASCII table, right there. So we have the ASCII code. So we have we'll see the ASCII code not so much this semester because we won't get to the point where we're writing code to send out to LCD displays or to terminals or anything here. But you will see it in the next semester in the microcontrollers. You'll see that there. If you're writing microprocessor code to run on a desktop, then you might see some of that. We're going to be writing microprocessor code to run in hardware, so we won't see a lot of characters since we won't be interfacing keyboards or displays to our processor this semester. Okay, we get into the electronics area here. This is one of those areas. Again, this should be a review from digital. Most of this hour and a half will be a review of digital. That's there. If you're dealing with TTL voltage levels, then typically between 0.8 volts or 0.7 volts and 0 volts is considered a low. Now, that number should ring a bell to anybody who's taken a course in electronics. That happens to be the voltage required to turn on a transistor. Right there. That's the breakover voltage of a transistor. Right there. If you put 0.7 volts onto the base of a transistor, that transistor starts to forward bias, current starts to flow through it, therefore you start to draw current through from the collector to the emitter. So it takes 0.7 volts. Anything below 0.7 volts, that transistor does not turn on. That's it, where that 0.7 volts goes. That there. And then everything between 3 volts and 5 volts is considered a high. Again, that goes back to is if I measure the voltage on the output of a TTL transistor switch, it should be between 5 volts and 3 volts. 90% of the time, it's going to be closer to about 4.8 volts, 4.5 volts, right there. But it's got to be something greater than 5 volts. Now, this is for TTL level. Our boards are not TTL level. They're 3.3 volts. So the levels will change. That there. So, that there. This book was written, this is an older book. It deals with where the old 8051 processor was a TTL level. What you talked about in your basic digital course there. And I don't know, what did you do in labs in your basic digital course? Did you have a lab? That there. What did you even do a lab? Because they schedule my basic digital course without any labs. So I'm using the Altera boards is what I'm using for the labs. Nobody can remember what you did. Did you do any labs? Okay. I have to assume you probably didn't, since they're scheduled with no labs. They actually scheduled this lab with very little labs. So, okay. All I'm saying is that if we were to take a volt measure and measure with this particular board, we won't get 3 volts and 0.7. Those voltage levels are different. They're lower. So, but we're going to stick with right there. Okay, well, I'm going to just kind of, let me sit down here and just kind of skim through the next few slides so I don't have to walk through here. The AND gate, everybody knows what the AND gate. Now, the AND gate and the OR gate, you covered in basic digital, we will still use those this semester, only we will use the command and OR. Those are assembly language commands where we AND 2 registers together. So you still have to remember what AND and OR mean, because we will be using them. But they won't be gates here. They will be assembly language instructions that we could set there. Tri-state buffers, you do need to know what a tri-state buffer is. Now, this particular one, they don't show the tri-state buffer, and I don't think I can write on this particular screen. I'll see if it'll let me write on this screen. Oh, okay, it does let me write on the screen. A tri-state buffer is basically shown without the bubble here. And then we have another pin for the enable right there. Usually an output enable right there. Right there. And what this particular gate does right here is that if this signal is active, and there may or may not be a bubble on this right here. If there's a bubble on that, then it means it's active low. If there's no bubble, it means it's active high. That's there. So that means if this is active, and I'm just going to use the word active to mean if there's no bubble, it's active low, it means that that signal is low. If there is a bubble, it means it's active high, it means that input is a 1. So that means that if there's a 1, there's a 1 out here. If there's a 0, that means there's a 0 out here, right there. Whatever's here is just passed through if the output is enabled, right there. And you may see output enabled with a bar across it. That means also the same as there's a bubble. In other words, it's active low, right there. If there's not a bubble, if this is not active, the output here is what they call a high Z, or a very high impedance, right there. And that's a very important type gate when we deal with microprocessor systems, is that we have to be able to connect or disconnect certain devices to our circuit. And to give you an example of that real quick is we've got something here called the data bus. It's the data bus. And excuse my handwriting, I'm trying to write over a keyboard here. The data bus is connected to all kinds of different devices right there. You know, this is a memory device. This is an input-output device. This is the processor. This is another memory device. All kinds of different devices are tied to this data bus. Only one can write to the data bus at a time, because if this tries to write a 0 and this tries to write a 1, things burn up. So we have to disconnect everything but one device at a time to talk to this particular data bus. And the way we do that is with the tri-state buffer. That's there. So you probably didn't cover it much in your digital course. That's there. But it's a way of connecting or disconnecting something to a device. Now, when we look at memory, quite often our memory devices and a lot of our peripheral chips will have a pin called output select or output enable or chip select or something like that. That means that the tri-state buffer is built into the device. But the idea of the tri-state buffer is that there's 3 particular outputs. The output could be a 1, a 0, or high impedance. That's why it's called tri-state. There's 3 particular outputs right there. 1, 0, Z. In other words, Z is the high impedance. That means it's neither a 1 or 0. It's essentially disconnected from the circuit. And when we start putting some of our circuits together, we have to be able to do that. And I will revert back to the 8086 in some of my discussions on hardware, but we won't spend a lot of time on that. The inverter is the same. The XOR is the same. Right there. The NAND gate's the same. The NOR gate's the same. Those are all basically the same, and I'm not going to waste your time going through those right there. So, again, we have the half adder, the full adder. Again, I'm not going to worry about too much of that there. There's the 4-bit adder by tying together 3 or 4 full adders right there. And I don't know if you've seen this particular circuit or not. I know I just did it when I just taught the digital course. I made them go through this particular circuit right there. But we have the full adder. You know, I make them do it with Altera, where we could actually we actually hook it up right there. That was actually the first lab second lab in the digital course. All right, decoders are very important, and I'm just talking about them in the digital. I don't know how much time you spent on there. They're basically used for address decoding, and they're used with the idea, then going back to, I have a processor, microprocessor. You'll see that term microprocessor. I have some memory devices over here, right there. I have, coming out of this microprocessor, and we'll see this in more detail, I have something called the address bus. The address bus tells me which memory location I want to look at. Now, if you look at it in terms of your home address, it's the same type of thing. I have a location over here, and it's got an address there. And each particular device here has a bunch of addresses, FFFF, down to say F000 right there. So any address that's between that range is going to reside in this chip right there. So in this chip, there's the addresses 000FFF right there. Right there, inside that chip there. So I have to be able to select which chip is this chip here. And we'll go through this again. And the way I do that is I have a decoder. And this particular one is going to be a 16 to 1 decoder right there. Or 1 to 16, excuse me, I got that messed up here. 1 to 16 right there, where I have, excuse me, this would be 4 to 16. I have 4 inputs right here, and I have 16 outputs right here. So I have 4 inputs, 16 outputs right there. And if these outputs are 1, 1, 1, 1, I'm going to select this device right here. Right there. If it's 1, 1, 1, 0, I select the next device. And we'll see these circuits in more detail. But what a decoder does is, in this particular case, 1, 0, 0, 1 right here, that if the address is 1, 0, 0, 1, this device output is going to be high right there. Here it's going to be 0, 1, 0, 1. Again, note the least significant bit. That means that this device is going to, that output is going to be high in this particular case. This is how we're going to address different memory locations or I/O ports, is that we use these decoders. So you cover the decoders in your basic digital class. This is where we would use it from our hardware standpoint. Again, keep in mind, this is the most significant bit, so I write that one here. So I started at the bottom writing up that there. And the only way I know that is because the author put the LSB here. Right there. That's LSB is least significant bit. MSB is most significant bit. So you'll see those terms, LSB and MSB. And I'm going to just kind of put that here. I'm going to rewrite this here as 10010011. This is the MSB right here. This is the LSB right here. So this is the highest value. That's the same thing as if I put down the number 326. 3 is the most significant digit right there. Right there. 6 is our least significant digit right there. So the 3 has a higher value than the 6 in our number. So when we go back to our digital world, we look at the fact that this is our least significant bit, so we write this one first, going this direction, right there. And the only way we know that is we see the least significant and most significant bit. And again, you should have seen this in your digital course. You probably forgot that looking at some faces there, right? That there. And by all means, when you see a term you don't know, that's the time to stop me and ask me to explain it. Don't wait till I get to the end of the lecture and say, what does LSB stand for? Stop me then and there. I don't know if all of how your instructors are. I've never taken a class from a Malaysian faculty member. At least I've taken them from Indian faculty members and British faculty members. I went through graduate school with a lot of foreign faculty members. I don't know how good they are at stopping in the middle of the lecture and asking questions. I am a big fan of stopping me right then on the spot and getting it clarified before I go any further. And if I use any English that you don't understand, the same thing. Don't let me go too far in that there, because you're paying good money to sit here, or someone's borrowing good money for you to sit here to learn this material. And if you don't understand what I'm saying, someone's not getting their money's worth. Right there. So by all means, stop me. Not there. Okay. Flip-flops. We won't be using a lot of flip-flops in this class. Flip-flops, we'll look a little bit at flip-flops because they're used for memory devices, but for the sake of this course, we're going to treat memory as memory. We're not going to worry about what's inside of it. That's there. We'll talk a little bit about the difference between static RAM and dynamic RAM, where we'll talk a little bit and come back to the flip-flop when we talk about memory, but we're not going to be doing any flip-flop circuits. That there. So everything you learned about flip-flops in the past, you can forget for the next 14 weeks. Right there. Okay, some terminology that we use right here. A bit is a single binary digit. It's either a 0 or 1. A byte, and let me just do it in the order of size. A bit is a single 1 or 0. A nibble is 8 bits. Right there. I tend to think of it as a cookie. You take a bit, is a small byte. You take a nibble, which is a bigger byte, and then you take a full byte, which you take the whole cookie. Right there. Then they changed the word, which is now 2 nibbles or 2 bytes. So, bit, nibble, and byte makes sense when you look at the cookie, but then they go to word and double word. And also not shown on there is a quad word. A word is 16 bits, a double word is 32 bits, a quad word is 64 bits. Right there. We're using an 8-bit processor, so normally we're going to be working only in bytes. Bytes are the standard size for memory and everything else. So when you do hard drive and memory specifications, a kilobyte is 2 to the 10th bytes. Right there. A megabyte is 2 to the 20th. A gigabyte is 2 to the 30th, and a terabyte is 2 to the 40th. You'll find that those terms do not match exactly with your normal engineering notation. Engineering notation, normally a kilogram is 1,000 grams, right? A kilobyte happens to be 1,024 bytes, a little bit more. Same thing with a megabyte, tends to be 1,024,000 bytes or something like that. It's a number other than 1 million. Same thing with a gigabyte, it's supposed to be 1 billion. A terabyte is supposed to be 1 trillion. Right there. Now, those are the terms that you see most often with computer systems, right? Now we're looking at, most computers are typically looking at memory in the megabyte range. If you buy a brand new computer, it's going to come with between 4 and 8 megabytes of RAM. That there typically, you'll hear that term. Most desktop computers, you can put as much as 32 gig of RAM. Is usually about the most you'll see in a desktop. There are computer systems out there that will take up to 64 gig of RAM now, right there. When you look at kilobytes, we don't see that term very often anymore. When I bought my first IBM computer, my first real computer, it wasn't my first computer. I bought several toys before that. I bought a Commodore VIC-20, a Commodore 64, and some other, small, inexpensive hobbyist computers. But my first real computer was an IBM PC 5550 or 5150, the original IBM PC that they made in 1982. It came with 64K of RAM, is what it came with. And it came with 2 floppy disk drives. Actually, I had to pay extra for the second floppy disk, that each could hold 320K of data. Right there. So Ks were, kilobytes were the most common terminology for memory back in the 1980s. Megabytes, I didn't start seeing megabyte hard drives. My first hard drive I bought was a 10 megabyte hard drive, and I think I paid like $600 for it. It was quite expensive right there. And I thought life was great. I didn't have to move floppies around back and forth anymore. I remember the first gigabyte hard drive that I came across. I was working for a company called Magnavox at the time, and we were doing a project for the Navy where we needed to store a bunch of data for reporting purposes. So we had to buy a gigabyte hard drive. It was the size of a small washing machine, and it cost $30,000 US. And this was in 1985. That's there. So when if you talk about $30,000 US in 1985, that would equate to about $150,000 US today, which would equate to, if you convert it with the current exchange rate, about 700,000 RM. That's there. So you're talking well over 500,000 ringgits of today's value for that one gigabyte hard drive. Terabyte hard drives, those didn't come around until much later. Nowadays, I think I saw that somebody is actually making a terabyte flash drive right there. So terabyte hard drives are fairly common in most computers. You know, I'm using a Surface. It doesn't have that big a hard drive. It's only got a 256 gig hard drive in it. But my desktop, I've got a couple 4 terabyte hard drives in that. No, 3 terabyte hard drives. So terabyte hard drives are very common. So these terminologies are becoming more I haven't seen the term petabyte yet. That's the next level. But I see the term petaflop, and I do see the term petabyte when I talk about when I see some servers like Google has so many petabytes of hard drive storage. It's not in a single drive; it's in a room this size. That there with many drives. That there. But these are there. The only thing to keep in mind that these terms are the same as you use in regular engineering notation, but they're not the exact same size. They're a little bit different. They're that there. And it confuses some people because quite often you will format a drive. They will sell a particular drive and they will use regular size. In other words, let's say you buy a terabyte hard drive, and that's going to be, you're thinking it's going to be this, and a bunch of zeros after that, and it's got that 24 there, and then when you format it in Windows, it actually gives you something less right there. And that's because Windows uses this notation, and the hard drive manufacturer used the other one. So sometimes you'll find that when you're dealing with computers that some manufacturers will use the other notation. But this is the normal way in the microprocessor, microcomputer, digital world that we use the terms kilobyte, gigabyte, kilobyte, megabyte, gigabyte, terabyte. Right there is that's what they mean in the digital world. They mean something different when you're talking about grams, meters. What else do you measure that there? Let's see. What's the liters? You don't use the term kiloliters that much, though, or megaliter. I don't hear that term used. Do you? Anybody ever? I've never seen that used. The term a dam holds so many megaliters of water. That there. You don't hear that. It would make sense because I see it in the U.S. that it holds so many millions of gallons of water. That there, or so many, that there. But you never hear this. I've never heard the term referring to this dam holds so many megaliters of water. I've never heard that term. But I see the term millions of gallons when they talk about the Hoover Dam, for example, in Arizona. Actually, the Hoover Dam is between Arizona and Nevada. But when you talk about a dam, how much water it can hold, they'll use the term millions of gallons. They don't say mega gallons, they say millions of gallons. But I've never seen the term megaliter. That there. There's no reason you shouldn't, right? I mean, it's a standard. It's a standard unit of measurement, just like a gram is, or that there. Now you'll see the term megavolt, mega amp, kilovolt. You'll see those in the electronics world. And you'll see the term kilometers. I don't think I've seen the term megalometers that there. Of course, that's a billion meters. That's a long distance. That's probably how you would measure the distance between here and the moon, right there. So you don't see the term. You see millimeter, and you see micrometer, and you see meter, decimeter, which is the oddball. You'll see decimeter, which is a tenth of a meter, and you'll see centimeters, which is also not a standard unit, right there. But you see the term centimeter quite a bit, but you don't see gigameters very often. But again, you'll see kilohertz, megahertz, and you'll see it in hertz right there. It's just it just dawned on me that I've never seen the term kiloliter or megaliter right there. Okay, now we're getting into that there. So as we get into the CPU, that is the core of our microprocessor. That's what does all the. If you tell the microprocessor to add two numbers, it happens in the CPU. You tell it to subtract two numbers or multiply two numbers, to OR two numbers, it does that in the CPU right there. That is what executes the memory set there. We have our input and output devices. That's what talks to the outside world. In other words, in our input and our output devices, for the sake of this class, are only going to be digital. But in the microcontroller course, our input and output devices could be analog, going through an analog to digital converter or a digital to analog converter. The processor we're using does have built onto the chip a D to A and an A to D, but we're not going to use that this semester. That there. You'll see that in the next semester. Okay, so, but other devices can be such things such as a keyboard, it can be a modem, it can be an Ethernet port. These are devices that get information from the outside world into that there. Now, they may be something simple such as a port that we just read, or it may be another processor or another digital device such as an Ethernet signal is actually run through its own processor on the Ethernet controller chip that will actually talk to that there. Memory, we have two types of memory normally in our computer. That there. One is called random access, the other is called read-only. I do not like those terms, but those are what we're stuck with. Random access means that we can read and write to it. I prefer the term read-write memory for random access memory. That's memory that we can change within the computer system that there as it's going along right there. It's temporary storage that there. When you turn it off, whatever stored in RAM is lost. Right there, it's gone forever. That's there. So this is random access memory. Now, when you buy memory to upgrade your computer, that's usually what you're buying is more RAM. Right there. Usually you're buying dynamic RAM and you buy sticks that are 4 gig, 8 gig each. And there's some 2 gig chips, but they're not popular anymore. At least not. You might find them around here because they're low cost. But this is temporary. That there. I prefer the term read-write memory because it's read-write. Random access means that you can access the memory at any point in time. Read-only memory you can also access at any point in time. So read-only memory today is also random access, but it's typically memory that is burned into a chip on the computer system. It could be memory that is burned into a flash memory chip that is also read-write memory, but you don't read-write to it all the time. Your thumb drive is an example of a type of ROM memory that you can program it to contain certain files. You take it out of your computer and those files stay there. They're not lost when you take it away from the battery, but it's still treated as ROM from a computer system. Right there. So flash memory can also be memory that is read-writable. So the boundaries between these terms get very fuzzy right there. But typically, the way that I define them is RAM memory is memory that is designed to be changed often and repeatedly within the normal operation of the microprocessor or computer system. ROM memory is memory that's designed to be programmed once and left alone, however, could be reprogrammed later on. How many people know what a firmware update is? Ever hear the term firmware update? You've never heard the term firmware update? Okay, let me explain what a firmware update is. You buy a DVD player from Sony. I have a Sony Blu-ray DVD player. that I bought in the U.S. I brought over. That there. It's got what's called firmware in it. The firmware is the software that drives the microcontroller within the player. A DVD player or a Blu-ray player has a microprocessor system within it. It's an embedded system. Same type of thing we're talking about in this class. It has its own built-in computer system within it. You buy it. I bought it in the U.S. I use it fine. I bring it over here to Asia. Well, Asia's got some funky things in it. It's a different code for if I want to buy DVDs off the shelf. If you buy DVDs off the shelf in the U.S., they're coded for Area 1. Asia, I think, is Area 7 or 8 or something like that. So if I buy a DVD in Malaysia and I put it in my player, it won't play. Because that's there. But I could get a firmware update that tells it not to look for that. That's there. So what it does is it replaces what's in the ROM in the Blu-ray player and changes the code there. Quite often you will buy a motherboard, for example. You buy a computer motherboard and it's filled with some defects. It doesn't work right with Windows 10, for example. So the manufacturer of the motherboard will send out a firmware update that will update the BIOS ROM on the motherboard so that it works with the new operating system. So it's a way of updating the ROM out in the field. And when I say in the field, I don't mean the paddy field. I mean away from the factory. That's a term that when we say out in the field in the electronics world, it's once it's been sold and it's in the customer's hands. It's a way of doing an update to the software in that microprocessor-based embedded system without having to bring it back to the factory and do an update there. So it allows you to update the software within there. For a long time, a lot of the DVD burners, and I know I'm an old person, and nobody uses DVD burners anymore, right? Flash drives, thumb drives have kind of replaced the DVD burners, right? But back when DVD burners first came out, some of them wouldn't work with certain brands of DVDs unless you did firmware updates. You would be quite often, you'd buy a box of DVDs and they wouldn't work with your burner. You would instantly go to the manufacturer's site and see if there's a firmware update to update the DVD burner and update the firmware in the DVD burner. Those are all ROMs within an embedded system that you would do the update out in the field with. Back many years ago, when I bought my first IBM PC, the ROMs were chips on the motherboard. And if you wanted to update the ROM on the motherboard, you actually took out the chip and put in a new chip. And many of us did that from time to time with various motherboards, that if we wanted to use it with something, we would have to do a BIOS update, which meant that we popped out the chip and put in a new memory chip. So the firmware updates are much better, today over you download the update, you stick in the thumb drive before Windows comes up, it boots off the thumb drive and it installs the update onto the motherboard. And I've had to update many, many motherboards over the years because it wouldn't work with a particular brand of video card or something like that. If you put a lot of systems together, you learn how to do firmware updates. So firmware updates is a way of rewriting the ROM is what it is. When you look at desktop computers, the ROM in your desktop computer is what's called the BIOS. When you turn it on, it's got that basic input-output system. That's in the ROM chip. Everything else you load is in the RAM. When we deal with embedded systems, 90% of our code is going to be in ROM right there. The code we write to is actually going to go into the ROM on that board that I passed around. I don't know if it came back to me on this board here, or I didn't pass it around. On this board, there's the ROM inside this board right there that we write to. And we'll get into that in more detail. But these are the two basic types of memory that we have, RAM and ROM. RAM is temporary, ROM is more permanent. It stays there for a much longer period of time. Right there. And what am I doing here? I keep forgetting that I'm not running out there. Okay, this is kind of the basic And let me see something here real quick. All right, I got another 15, 20. See, this also keeps track of how long I've been talking. Right there. As I said, I normally talk about an hour and 15 minutes to an hour and 30 out there, so I can keep track of how long the lecture is. My time starts when I started recording. Right there. Okay, again, this is kind of the basic overview right here. This is a better example of what we talk about. This is on a desktop computer system right here. This is based on a normal computer out there. We have a CPU, and then we have 3 buses. And when we talk about buses, we're not talking about the bus from KL to JB. Right there. We're talking about a series of lines. The address bus varies by microprocessor size. The data bus varies by microprocessor size. The control bus is pretty well fixed. Right there. The data bus is typically 8, 16, 32, or 64 bits wide. When I say 64 bits wide, that means there's 64 wires going between the memory and the RAM and the ROM, not necessarily the printer, disk, monitor, and keyboard. Those really should not be shown on this diagram as being tied directly to the data bus. I stole the slides, and now I'm going to criticize them. That there. And the reason is that normally these devices here, right here, the disk is actually going to go through a disk controller right there. There's a circuit that is tied to the data bus and the address bus that will talk to the disk. But going to the disk itself, most disk drives are serial anymore. They're either serial ATAs or they're USB external disk drives. So they'll go through a serial port, but there's a disk controller that actually, if we change this to disk controller and monitor and video adapter, then that would be fine right there. So the printer and the keyboard today would go through the USB port. There would be another circuit shown on this today that would show the USB port. Really, at no time did I ever use a system that the printer was tied directly to the address data bus and control bus. It always went through either a serial or a parallel port right there. So it went through. So if you look at this particular slide, it's got some issues here. That RAM, ROM, and is true right there. If you look at this one right here, but the peripherals right here, there's actually going to be some additional hardware on the motherboard that will actually talk to those devices. And it may or may not be on the motherboard. If you're talking a standard computer system like the one sitting there by your knees right there, you're going to have on the motherboard, you're going to have a serial adapter or chip that drives the USB ports. So the USB ports are going to be talking to your printer and your keyboard, right? That's there. So you're going to see the USB adapter, and that's going to be a chip on the motherboard. We probably won't talk much about that in this class. There will be also a disk controller that there, which will talk to the serial ATA ports on the motherboard. Most motherboards have between 4 and 8 serial ATA ports on them. These serial ATA ports are serial. You don't remember what the ATA stands for, but they're adaptive transfer, tables. They're tables that go between the disk drive and the motherboard. The motherboard will have, now you can have add-on cards that will give you additional serial ATA ports right there. But most disk drives will connect up to a serial ATA port, and it goes to the serial ATA ports on the motherboard right there. And has anybody here ever taken a computer apart and put one together? You see, that's the difference between classes. Usually when I talk to a class in the past, almost everyone's taken a computer apart. I'll have to find see if I can get my hands on a couple motherboards and bring them in so we can see that there. I think it would be useful that they're bringing some components that there. Let me see if I can find an old computer I can cannibalize that there. There's got to be some around here. I think the LabTech's got some that there. I just want to cannibalize because it's a little bit easier if you see what I'm talking about. That's there. But all I'm saying is that everything from here over does not connect directly to the address data bus and control bus. They go through other controllers right there on a modern system. That there. They don't tie directly to the processor. There's something in between there. Now, what's in between there will tie to that. But when we look at the keyboard and the printer, that will go through the USB ports. And again, a USB port, you've seen enough of those over the years. And maybe I find it easily. I mean, that's a standard USB cable right there. That happens to be USB 3, right? And that goes into a controller there. And then you can have additional USB hubs right there. Well, built into the motherboard, there's a hub that talks directly to that there. So that there. This slide was done probably back in the early days of computers where USB wasn't popular yet. That there. And back in those days, printers actually were tied to a parallel port on that there. You had to worry about interrupt numbers and getting printers to work, getting modems to work, and all that stuff was a pain in the neck. Those of you that think Windows is a pain in the neck and get mad at Windows really need to go back to, back to the early days of computers, back when you ran on DOS and figured out how much of a pain things were then. It's actually much, much easier today, even though it's still not perfect. Although if you talk to somebody who owns a Mac, they'll say that Macs are perfect, but I've had a Mac and they're not perfect either. They're far from perfect. But the thing is we're going to be talking about these three buses. Even though I picked on these slides, these three buses are very important there when we talk about that there. So a bus carries a place out there. The address bus, the size of that, will tell you how much memory space you can have, the processor can support. If you've got, for example, 16 lines that they're in a memory on a memory bus, it means you can address 64K roughly of memory. If you've got 20 lines, you can address about 1 meg. If you've got 24 lines, you can address up to like 4 gig. If you have 32 lines, you can address that there. So the number of address lines makes a difference right there, is how much memory you can support. Now, if you've got a 32-bit version of Windows, it will only support up to 4 gigabyte of memory because that's all that the 32-bit version of Windows was talked to. That's the limitation at the time it was written, 32-bit. When you go to the 64-bit, then it can address much more. The data bus here, this is how much data, the width of the data bus is really how much data you can move in and out. That's there. If you talk about an 8-bit processor, you're saying that particular 8-bit processor will transport data 8 bits at a time. Look at it as a highway. It's got 8 lines of traffic. Now, the data can only move in one direction at a time. So the processor's either writing to the data or it's reading data from somewhere else. Remember I said that only one device can write to the data at a time. So this tells you where, and this contains how much. The address bus tells where you're writing or reading to. The data bus is where the information is actually transferred to. So the address bus will talk to all these various places in memory, and the data bus will actually move the data around right there. The control bus is the traffic signals. It says who's going to write when and where. And we're going to spend some time looking at these various buses. Right now, I just want to point out that there's these three buses. Ignore parts of this right here, because those parts here, you just put one on there called I/O right there. I/O is a large category that includes everything from disk drives to keyboards to monitors to thumb drives to printers to scanners to digital cameras to cell phones, whatever else you plug into your computer. All right? I plug my cell phone into my computer all the time, you know, because I download podcasts into iTunes that I want to that I want to transfer to my phone to listen to in my car. Bluetooth also falls under one of these, and Bluetooth is another communication method. I'm using Bluetooth right now. Bluetooth is how this is getting the signals getting from this little funky thing in my ear to my computer to record the audio, right there. Bluetooth is how my pen is talking to this to the keyboard. So Bluetooth is another input device or output device. I can put on Bluetooth headsets. I carry a pair of Bluetooth headsets around here, and I can put a movie on my laptop computer and sit outside and listen to my wife yell at me actually I don't listen to my wife yell at me because I put the headphones on so I don't hear her, and watch a movie and smoke a cigar in front of the house. I've discovered that most Malaysian women can't stand the smell of cigar smoke. Of course, most American women can't stand the smell of cigar smoke either. Or what do you call it? Shroot is the term in Malay for a cigar. Shroot. Morocco is cigarette, right? Morocco. But cigar is what? Shroot. You know, I smoked the nice, big, thick, round ones I smuggled from. I didn't smuggle. You're allowed to bring so many in from the U.S. and every now and then I'll go through in front of my house and light up a 7-inch cigar and smoke it. That's my one bad habit, right? That's there. So I probably have more than one bad habit, but that's my primary bad habit. But I use a Bluetooth stereo headphones and watch TV shows that I've downloaded to my laptop, and I'll watch them outside. So I use the Bluetooth as an output device in that case. Here I'm using it as an input device. There. So Bluetooth is another type of device that talks to my computer. And the reason I bring these up is because as we go through and look at microprocessors, we have to understand all the various types of inputs and outputs we can have. And this drawing here is very, very dated because it doesn't show all the ones we have there. So, okay. And I think I'm probably nearing the end. Oh, no, we got another 5-10 minutes here. Okay. Let me finish. Let me talk about the buses here. That there. And we talked about that there. So, for everything there that we want to talk to, it must have an address bus. The address must be given to a particular device or memory location. One device can have many, many addresses. If you have a 4 megabyte memory chip, that means it has 4 million addresses to that device, right there within that device. So you have to have the address lines to address those 4 million addresses brought to the device. Some devices are given a unique and a single address. When I connect this Bluetooth up to my computer, it's assigned an address by the computer. I don't know what it is, but it's given an address. So that when I talk, it knows that signal gets routed into the audio processor. When this thing talks to it, it gets routed to the digitizer, which is treated the same as a mouse, right there. So, and the same thing with my keyboard if I use my finger to move back and forth, right there. So, that is for any input or output device or memory has to be assigned an address. Now, in the case of Bluetooth and disk drives and that, typically the memory device, the address is that of the controller. But we won't get into that there. The data bus is where the data is sent back and forth, right there. That there. And the control bus controls the various signals right there. The larger the data bus, the better the CPU. I hate that term. I sold the slides and I should rewrite them and then give them credit and rewrite them and improve them. The larger the data bus, not the more data buses, that's bad English anyway, but this guy's from Taiwan, so I won't pick on his English. But the larger the data bus, or the more lines there is in the data bus, the more data you can move at any one time. If you have a 32-bit data bus, it means you can move 32 bits of data into the processor, in or out, right there. The processor we're going to be using is going to be an 8-bit data bus. Those that used to teach this class, they used to use a 16-bit data bus with the 8086, 16-bit data bus. That there. So the average size of data buses varies between 8 and 64 bits. right there. Now, that's how much data you can move back and forth. Now, I don't like the term better because better means what's optimal for the particular job. If you're designing a desktop computer system that you're going to be editing videos with, by all means, you need a 64-bit processor. You need as much horsepower. How many video game players do we have now? Somebody's going to raise their hand, right? How many people play video games? Yeah, I saw it go up. Yeah, I mean, it's okay. But video games are very graphic intentional and have lots of graphics to it. That's there. And if you play video games, you need a very expensive video card unless you get jerky graphics, right? That's there. Same thing with phones. How many people have ever played video games on a phone? Right? Yeah, I mean, I know people do it. I'm not into video games. I'm of the generation that they came out. My kids played them. I tried them for a while. I sat down. Got there. My thumbs got sore. I got to the point. Now I get arthritis in my thumbs if I try to play them. So that's there. But regardless, I understand the concept of them, and that there. And I can sit and watch people play them for hours, but I just don't play them. That's there. And that's there. And actually, people 5, 6 years younger than I am, I know that are really into video games. I know people in their early 50s that really got into the video game craze that are just a few years younger than I am. That there. So I'm just at that age that they weren't quite easy. I played some of the early games. I think Wolfenstein might still be out. Some of those games I played. That there. But regardless, if you're playing video games, today's video games require a lot of horsepower. The most expensive desktop computers you can buy are for gamers. I mean, if you buy a gaming laptop or desktop computer, you're spending 6,000 to 7,000 ringgits easily, right? That there. If you want a high-end gaming system, that's there. I don't have a high-end gaming system. I have a high-end system that I use for editing videos for courses like this. Now, these classes I don't edit. I just record them and just encode them. That there. But even then, they take a half hour, 45 minutes on this computer. At home, they take like 5 minutes on my system. That there. So, but this is a i5 64-bit processor, so this is no slouch either. But you need something like that. That there. Data buses are bidirectional. The processing power of a computer is related to the size of its data bus right there. Now, the address bus means the more devices or memory locations it can address. Normally, the bottleneck is not the number of I/O ports, but it's the number of memory locations. If you look at the original 8086 processor, which this course used to be taught on, it had 20 address lines. 20 address lines means that you can only address 1 meg of data. That's a joke today, right? For a desktop computer, 1 meg of data is a joke. Nobody has a system that's down to 1 meg. Even 2 gig is getting too small for most people. That's there. I know some people that still have 2 gig. I think these systems might have 2 gig or 4 gig in them. That's there. I know that the laptop that I was issued had 4 gig. That's there. But regardless, that's there. So 24 address lines, which was the 186 address, up to 16 megabytes of data. Every time you add another line, you double the amount of memory that you can address. So if you go 25 lines, it's 32 meg. 26 lines, it's 64 meg. And you get up to where you got like 32 lines, you're getting up to around 4 gigabytes or so. Because 30 lines will get you 1 gigabyte. So 31 lines gets you 2 gig. 32 lines will get you 4 gig. So the original Windows 95, it was a 32-bit operating system. It only went up to 32 lines, is all it would address, so it would address up to 32. So if you have a 32-bit operating system, it will only recognize up to 4 gig. If you put more than 4 gig in there, the system won't see it. So you have to go to a 64-bit operating system, which will then see the additional memory right there. So again, that's the amount of memory. The address line, and this is the important one here, is unidirectional. Only the processor writes to the address line. Only the processor. Remember, the processor does everything in terms of telling the information where to go and what it's supposed to be used for. It does. The CPU does all the calculations and everything, and the processor directs all the traffic right there. So the data bus is how much we're going to move. The address line tells us where it's going to move. Now, the address line is not the only part of the address, and we'll talk a little bit more about that. I think I'm going to wrap this up here, even though I'm going to come back to this, and the reason is in a half hour I need to start and repeat this whole thing again. So